In this set of notes, we're going to look at trigonomic limits and the Sandwich Theorem. Just to start with, the first thing we're going to do is just review different trigonomic functions. So a trigonomic function is a type of periodic function, and so let's first define periodic functions. A function f of x is periodic if there's a positive constant a such that f of x plus a is equal to f of x for all x in the domain of f. If a is the smallest number with this property, we call it the period of f of x. So what exactly does this mean? One way to think about it is that we can break the x-axis into sections of length a, and the function will look the same at each of the sections. So let's look at the example that we have here. So first of all, notice that this function, if we look at it, it looks like the pattern is repeating. So for example, if I were to draw a vertical line from here, actually let me make that line just a little bit thinner. If we were to draw a line here, and then draw a line here, we can see that the function is repeating itself. So in this first section, we see this pattern, and then the pattern repeats itself. And if we were to have the x-axis to be longer on both the right and the left side, we would continue to see that pattern repeating and repeating over again. So the smallest interval that we can draw where this function is going to repeat itself each time, that is what we call the period. Now, the other thing to notice here is where I draw those vertical lines, there are really an infinite number of places that I could draw them, but for example, notice I could have just as easily drawn the vertical line here and here. And that length, or that width, I guess I should say, of width A is the same if I were to draw the vertical lines like I have them here, or if I went back and I drew the original vertical lines that I have. So in other words, in either case, the period is still width A. And so that's what it means for a function to be periodic. In other words, it's going to repeat itself over and over again across the x-axis, and that width at which it repeats itself stays the same. All right, so let's look at a couple examples, and let's see if we can determine if either of these is a periodic function. So we'll start with the one here on the left. One of the important things to notice with this function is that we have these two arrows. And so notice this function, because of these arrows, is just going to continue to go up and up and up. And so notice there's no way for it to repeat itself throughout the x-axis if we were to look more to the right or more to the left. So this one is not periodic. On the other hand, if we look at the plot on the right, notice that we do see a repeating pattern. And so for example, I could draw a vertical line here and here, and notice that this pattern continues to repeat. And so again, the width here, that would be the period. But again, notice that I could have just as easily drawn those vertical lines here and here, but that width would still be A. And so again, that one is a periodic function. All right, so the trigonomic functions, here are 6 of them. We can see that they are periodic. So in other words, they are going to repeat themselves as we go up on the x-axis to the right and down to the left. Now, the one thing to notice is that, as a reminder, if it's been a while since you've seen trigonomic functions, we typically look at them in terms of pi. These are really useful when we're working in geometry, and so the reason that you see on the x-axis you see these in terms of pi is often with trigonomic functions what we're really working with are circles. And we'll also, within those circles, we can look at angles, and then that relates to triangles. So the trigonomic functions are really useful when it comes to geometry. But again, notice that each of these is a periodic function. We do see that repeating pattern as we move along the x-axis up or down. Now, the trigonomic functions, sine, cosine, and tangent, do show up throughout biology. In particular, when someone attempts to model a periodic phenomenon such as rainfall over the course of a year, the rate of growth of population of cells that have a circadian rhythm, and so that's one where the growth changes predictably over a day. And so we might want to look at the rate of change of those functions. But to do that, there are a couple of different trigonomic limits that we do need, and so we'll need these later on in the future. And so your book gives a geometric argument for these limits. You're more than welcome to read that geometric argument. I'm not going to cover that. Instead, I'm just going to focus on the sandwich limit theorem. And you will find in general, your book is going to cover these more in detail than I am. I'm mainly just going to focus on the overall idea of the sandwich limit theorem and how we can apply it, not so much the geometry with the trig. All right, so suppose that I wanted to find the limit of this function right here. And so you'll see here that I have a plot of it. And so notice that if we were to draw a vertical line at x is equal to 0, you'll notice that here on the function we do have an open circle. And the reason for that is the value x equals 0 is not in the domain of this function, because we have an x in the denominator. And so remember, when x is equal to 0, we can't have a 0 in the denominator, and so that's why 0 is not in the domain. Now, looking at the plot of this function, we can see that as the function comes in from the left, it approaches 0, and as it comes from the right, it also approaches 0. And so, as we've seen previously with other functions like this, when we think about the limit, we're not looking at the function evaluated at 0, we're looking at it as approaches 0 from the left and to the right. And so for that reason, using the graph, we can see that the limit is 1. But the question is, how could we prove this more formally, other than, just visually looking at a graph? What could we actually write down, to show or to prove that that limit is equal to 1? And so to do this, we have to be kind of clever, because we can't actually work with the function itself. Instead, what we do is we're going to employ what is called the sandwich, or also known as the squeeze theorem. So your book is going to call this sandwich theorem, but if you look it up online, it'll often be called squeeze theorem. And so here is the basic idea of the sandwich theorem. So the sandwich theorem, what it does is it says, okay, if we were interested in learning about the limit of g of x, so this is the function that we're interested in. So like in the previous page, we had that sine of x divided by x. What it says is if we can find two other functions, and so we're going to call them f of x and h of x. Now the use of f, g, and h here, that ordering, once you define these isn't actually important. What is important is that you're able to take the function you're interested in, so here we're just going to call it g of x, and you find a function that is always below it, and a function that is always above it. And this doesn't have to occur everywhere. It just has to occur on an open interval that contains c, which is the value you're interested in looking at the limit at. And so if you can do this, and the limit of f of x exists, and is equal to the limit of h of x, essentially what this is saying is those two limits are kind of like the bread, and g of x is the meat of the sandwich. And so if the two bread pieces touch, in other words, they're equal to one another, then the limit of g of x must also be equal to that value. And so that's why it's called the sandwich or the squeeze theorem. And so I think it's kind of easier to see here in a picture. So let's say in this picture, we're interested in the function f of x. So in this case, go back to my highlighter, I'm interested in f of x. And so notice for this case, if I'm interested in f of x, I can see, looking at this plot, that h of x is always going to be greater than f of x, and g of x is always less than f of x. So this is what I was saying, don't get too hung up on the use of g, f, and h. What's really important is the ordering. Well, if this is true, then I know that the limit, and so here we're going to be interested in c, as x approaches c of g of x is always going to be less than or equal to the limit as x approaches c of f of x is going to be less than or equal to the limit as x approaches c of h of x. And here we can see that the limit of h of x, we're going to assume that that's equal to L, and the limit of g of x is also equal to L. So then automatically the limit of f of x is also going to be equal to L. So in other words, we can see that these three functions, when it comes to being evaluated at c, they all are approaching L. And since h of x is always greater than f of x and g of x is always less than, and they're equal to one another, then we know the limit of f of x has to be equal to L. And so this is just a picture of exactly what this is saying, except the picture just orders the use of g, f, and h differently. All right, so let's look at an example of what this would actually look like. So to start out, notice in this example, we have that 1 is always going to be less than or equal to f of x, is always going to be less than or equal to x squared plus 2x plus 2. So notice that this information, the problem is giving you this information. So this is what we call given information. And the goal is we want to find the limit of f of x as x approaches negative 1. So notice that I've got three different functions here. So what I'm going to start out by doing is I'm going to let g of x be equal to the first function. So g of x is just going to be equal to 1. And I'm going to let h of x be equal to the third function. And then further notice we are given that 1 is less than or equal to f of x is less than or equal to x squared plus 2x plus 2. But I'm going to let g of x be equal to 1, so I know that g of x is less than or equal to f of x is less than or equal to h of x. And now since we're given that, and this holds true everywhere, we also know that the limit as x approaches negative 1 of g of x is going to be less than or equal to the limit as x approaches negative 1 of f of x is less than or equal to the limit as x approaches negative 1 of h of x. Okay. So next, if I can find this limit and this limit, if they are equal to one another, then I will automatically have the limit as x approaches negative 1 of f of x, which is what I want. So we'll start with the limit as x approaches negative 1 of g of x. Well, remember that g of x is just that constant function equal to 1, so obviously that's just going to be equal to 1. And then I also want the limit as x approaches negative 1 of h of x. And so just going back up here, remind myself, h of x is equal to x squared plus 2x plus 2. And so this is where I can use those limit laws to break up this limit to show what it is. So here, notice that what this is going to become is I'll have the limit as x approaches negative 1 of x times the limit as x approaches negative 1 of x. So that's the x squared term, because x squared is really x times x. So that's equal to the limit of x times the limit of x. Plus 2 is a constant, so I can pull it outside of the limit. And then again, we've got the limit as x approaches negative 1 of 2. And so we can see this is going to be negative 1 times negative 1 plus 2 times negative 1 plus negative 1. And so we end up with 1. Oh, sorry, this last one is not negative 1. That should be a 2. So we have negative 1 times negative 1 is 1, minus 2 plus 2 is equal to 1. So notice the limit of g of x is 1, the limit of h of x is 1. Up here, we know that the limit of f of x has to be greater than the limit of g of x, which is 1. And the limit of h of x is 1, and f of x has to be less than that. So in other words, this limit is sandwiched between 1 and 1. So therefore, the limit as x approaches negative 1 of f of x is equal to 1. And so we've shown what we need to show. So here's another example. Now, for this example, we're going to go back to that function that we saw earlier. So we're interested in the limit as x approaches 0 of sine of x over x, and we want to show that that's equal to 1. And we're going to do this using the functions cosine and 1 over cosine. Now, if you read in your textbook is actually going to talk about the choice of those functions, and it is related to the geometry. I'm just going to kind of gloss over that here, but if you want to see where these functions come from, you're more than welcome to go read that section in the book. So if we look here, we have a graph of these three functions. Now, in red, we have sine of x over x. In the blue, we have cosine of x. And then in the green, this is where we have the 1 over cosine of x. And so we're going to try to use the sandwich theorem to help us. But you might look at this and say, wait a minute, I'm interested in the sine of x over x, but I notice that cosine of x crosses over it. So it's not always either less than or equal to sine of x over x, it kind of fluctuates. Well, remember, to use the sandwich theorem, we only need to have an open interval around the value that we're interested in. So notice that we're interested in the limit as x approaches 0. So I'm going to draw a vertical line over where x is equal to 0, so that's here. And then, change my pen color here. If I only look at, let's say, this interval here to here, notice that inside of that yellow box, we have that the cosine of x is always less than sine of x over x, and 1 over the cosine of x is always greater than sine of x over x. So inside of this open interval, we have the inequality that the cosine of x is always less than or equal to the sine of x over x is less than or equal to 1 over the cosine of x. So in this open interval, this inequality holds true, so we are going to be able to apply the sandwich theorem. And so that's why it's important with the sandwich theorem that we make sure we don't forget about that part. It just has to be on an open interval around c, which is that value we're looking at the limit towards. It doesn't have to be over the entire domain of x. All right, so now let's see how we can actually show this. So again, from the graph, we can see that we have the following inequality. But we need to make sure that we also specify that this occurs on the interval -1 to 1, which contains 0. Now, the choice of -1 to 1, I'm just choosing that for ease. I could have just as easily defined this open interval from -1/2 to 1/2. So the choice of the -1 to 1 is a little bit arbitrary. As long as it's an interval so that that inequality holds true over the entire interval and that interval contains 0, then we're perfectly fine. All right, so the next thing we're going to do is notice that this implies that the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine of x over x is less than or equal to the limit as x approaches 0 of 1 over cosine of x. So just like the previous example, what I'm going to focus on is the limit of the cosine of x and the limit as x approaches 0 of 1 over the cosine of x. So first, we're going to look at the limit as x approaches 0 of cosine of x. Well, cosine of x exists at 0, so we know that this is just equal to 1. And then next, we're going to look at the limit as x approaches 0 of 1 over the cosine of x. And we can use our limit laws to show that this is equal to 1 over the limit as x approaches 0 of cosine of x, which again is equal to 1, so we just have 1 over 1, which is equal to 1. So therefore, since the limit as x approaches 0 of cosine of x is equal to 1, we have that 1 is less than or equal to the limit as x approaches 0 of sine of x over x, and then that's less than or equal to 1 because of the right-hand limit. So therefore, the limit as x approaches 0 of sine of x over x is equal to 1. And then so again here as just one last example. So here we're interested in the sine squared x over x. So the first question is, why can we not use the basic rules to find this limit? So the reason that we can't use the basic limit laws is in order to apply the limit laws, we might look at something like the limit as x approaches infinity of sine squared of x over the limit as x approaches infinity of x. And notice that the bottom piece here is going to go to infinity. And we do have a limit law that helps us when the denominator goes to infinity, but the problem is that we need the numerator to go to a finite number. But this is going to oscillate between 0 and 1 because it's a periodic function. And so we're actually never going to get this to go to a finite number in the limit, so it ends up that we can't use our limit laws. But we can use the sandwich theorem to help us prove this. And so I'm not going to go through the proof like we did on the last two, but we can just look at a plot and argue how this is going to happen. So here, if we look at the plot, in red, we have the function 1 over x, and in purple, here, I've got the function 0. So here we could say that g of x is equal to 0, and we could say that h of x is equal to 1 over x. Now notice, as we move to infinity, 1 over x, or h of x, is going to keep on getting closer and closer to 0. And then of course g of x is just equal to 0. And then what is happening to our function, that sine of x over x, which we have plotted here in the black, it is getting progressively closer and closer to 0, and it's sandwiched in between 1 over x and 0. So you can go through and formally show by the sandwich theorem that f of x is basically going to get sandwiched between g of x, which is 0, and 1 over x. And so that's how you would go about showing that its limit is also 0. And so again, you could go through a formal argument just like we did with the previous ones, and you would want to do that after looking at the graph. But looking at graphs of functions are a great way to kind of get an idea of, hey, is the sandwich theorem even going to work in this case? And in your homework, I've had you use Desmos. I think Desmos is a great, just quick way to make these plots and kind of look at, okay, is the sandwich theorem even going to be useful here? So this is going to conclude this set of notes. So as always, if you have any questions, you need any help, please let me know.